Hi everyone. So today I'm going to explain the first four questions of homework 5 in a linear algebra taught by Wei Chunshu. So before beginning with my explanation, I'll assume that you already have a clear grasp on various concepts regarding orthogonality, Gram-Schmidt of A is equal to QR reduction and other concepts related to orthogonality. So let's begin. The first question here is asking us is practically is just a question asking for a linear regression line that has the least square solution with respect to the points 7, -1, 7, 1, 21, and 2. These are the points that were given in the question. That is, this is RB and this is RT. So, and because we know the line already, we can plug in these 3 points and get these 3 equations. And since we know about the column multiplication, that given 3 vectors and 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 it's in a matrix form, and then there's another vector, if we multiply these two together, we'd get the A1 times the first row and A2 times the second row and A3 times the third row. This is our results. And if we apply this back into our equation, we get this equation here. And in fact, indeed, if you really multiply this back, you'd get this equation at the end. So now that we have successfully transformed these 3 equations into the matrix form, we can interpret this equation as Ax is equal to b. So now our goal is to find the x hat that such that our x hat is a projection of b, which is this vector, onto A, which is this vector, which is this matrix. Right, and from the textbook, we can actually derive that equation. You see, we can dissect our B into the sum of an error vector E plus an parallel component of the A matrix, which is denoted as P. So now we, forgive me, so now we move the P to our left-hand side, and we get E is equal to B minus P. So, but since our E is an orthogonal component to our matrix A, so we know for a fact that our A is in fact perpendicular to E. So we can derive A transpose E is in fact 0. And since we also know that our E is B minus P, we can plug this back in and get A transpose B minus P is 0. So if we open up the brackets and throw A transpose P to the right hand side, we get A transpose B is just A transpose P. And since our P can be further denoted as the A times a random vector x hat, so this is in fact A transpose A x hat, because our P is an parallel component of the matrix A. So that means the P is just an whatever scalar regarding is a scalar times our matrix A. So we can actually write it like this. So for solving for x, we just take the inverse of A transpose A and move it to the left-hand side, which at the end we'll get x is just A transpose A inverse A transpose B. So now that if we observe carefully, we already have our A, which is here, which is this one, this matrix. And we also have our B, which is this vector. So we can just compute for x directly. Forgive me. So I'll skip all these calculations and just show you the results. This is calculation for A transpose A, and we get this vector. So now when we take the inverse, we just apply the formula, which is the determinants placed on the denominator times the matrix with these two elements swapped and these two times -1. So this is our A transpose A inverse, and our A transpose B is simply the product of this matrix and this vector, and we get this result. So now our x hat is ultimately this, the product of this multiplied by this. So at the end we get 9, 4, which corresponds to our C and D in the line B is equal to C plus dt. So now if we plot the line, the blue line here is our regression line, and the yellow points are the points given in the question. And that's all for our question 1. So moving on. Question 2 has 3 parts. The first part is telling us to solve for P is AX. And since we know A and X already, we can just compute for P directly, which is the product of this matrix times this vector. And we get this as a result. And this P is, as I said before, is an parallel component of our earlier B vector with respect to our matrix A. So now, since we can denote B as the sum of P plus E, so that our error vector E is the difference of B and P. So now we have our P and we have our B earlier. We can just compute for our error vector directly, and we in fact get 2 minus 6, 4, which is exactly the vector that the question suggests. And now, why is big P multiplied by E is 0? So what is big P, first of all? First, the big P is a projection matrix that turns B into our small p. So our big P's job here is a transformation that turns B into the parallel component of B with respect to matrix A. So we can derive the relation as shown here. And since P is AX hat, we can write the equation P is equal to PB is equal to AX hat. And AX hat, as we all know, is A times A transpose A's inverse A transpose B. So now if we look at these two equations, like these two, you notice that there's a B on either side of the equation. So we can just take the B out, and our result is our big P is just A times A transpose A's inverse A transpose. Right? And then we slap on the E, and that results in A times A transpose A's inverse A transpose E. And since we know that E is an orthogonal component of vector B with respect to matrix A, so that means our A transpose E should be 0, right? So now we notice that there's exactly an A transpose E inside the equation. So this should be 0, therefore the entire thing should be 0. So our big P times E is just 0. Problem solved. Now, moving on to the third question. Third question is actually just telling us to solve for use the Klein-Schmidt reduction formula to solve for our big Q. So we'll assume that our A1 is already in place. That is because we don't have any components in our big Q yet. So we'll assume that A1 is already fixed in place, and then later we'll adjust A2 and A3 in accordance with A1. You'll see what I'm doing later. So we have assumed that our A1 is already in place. So all we have to do is to turn A1 into a unit vector, which if we take the square root of 2 out of A1, like as shown here, the inside this vector, this new vector is in fact a unit vector. So this is just A1 is just square root of 2 times Q1. Now, with A2 and A3, we'll need to remove, like for example, for A2, we'll need to remove the parallel component of A2 with respect to A1, so that our Q2 is orthogonal to our Q1, right? So we look at this equation again, right? Our equation is B is equal to E plus P, and our error vector is B minus P, right? So, and our P, as we have solved earlier, is just A times A transpose A's inverse A transpose B. So the difference here is that earlier, we don't want the error vector E, we just want the parallel component P. But now things are kind of reversed here. We don't want the parallel thingy P, but instead we want to let the vector retain our error vector E. So what we're doing later is kind of in reverse of what we've done before. So you see, this is our B and this is our P, right? So because our A is in vector, so our A transpose A should be a number, or denoted as a constant. So this is just a number. So if we so the inverse of a number is just the number moving to the denominator. Forgive me. So our E is ultimately B minus A times A transpose B divided by A transpose A. So solving for E2, we get A2 minus A1 times A1 transpose A1 over A1 transpose A2. So what is this? This is A2 itself, and this is the parallel components of A2 with respect to A1. So we're subtracting the parallel components of A2 with respect to A1 such that our result should be orthogonal to our A1. So I'll skip all these calculations, like this is A2 and this is this thing here, this is this thing here, and at the end we'll get this vector. So this is just an vector that is orthogonal to A1, but it's not quite a unit vector yet. So we turn it into a unit vector, which is we take the square root of 6 over 2 out of the vector, and we get this as our Q2. Right. Forgive me. Oh dear. Sorry. Now for E3, it's kind of the same actually, but now we not only have to subtract the parallel part of A3 with respect to A1, but also we'll have to take out the parallel components of A3 with respect to A2. So we compute these two accordingly and subtract these results from our A3. And this is our parallel component of A3 with respect to A1, and this is our parallel component of A3 with respect to A2. And after subtracting these two, we end up with this vector. that is orthogonal to A3 and which is orthogonal to A2 and A1. But this is not quite a unit vector yet, so we take also our square root of 6 over 2 out of the vector, and we end up with this as our Q3. So now for clarity, I have written a Q1, Q2, Q3 as thus. And now when we combine these three vectors, we end up with our big Q, which is Q1, Q2, Q3, right? So our B is telling us to decompose for A is equal to QR. So this is our A, this is our Q, and this is our R, right? So of course you can use the Gaussian-Jordan elimination and solve for the inverse of this matrix and times that inverse on the left-hand side of either side of the equation and solve for the ultimate product. But that's too much of an hassle here, because this is just straight up ugly. Instead, my take is to use our column multiplication in reverse. So armed with the knowledge that that v1, v2, v3, a1, a2, a3 is just a1, v1, a2, v2, a3, v3. When we look at this equation here, we actually notice that if we take the square root of 2 of column 1, nothing for column 3 and column 2, we actually get our first column for A. So in fact, our first column of R is just simply square root of 2, 0, 0. Actually, this is also quite easy to understand here. Why? Because when we compute for A1 earlier, there were nothing for us to subtract the parallel vector components from our A1. So our Q1 is just simply a scalar of A1. So it is only normal that the first column, that is our A1, is just some scalar here times our first column, which is our Q1, right? So this is in fact this times the first column and nothing else. And we can say the same with the second column as well. We can actually just through observation, we can see that the square root of 2 over 1 times the first column plus the square root of 6 divided by 2 times the second column and nothing for the third will end up as our A2. Right. But the third column is a bit too complicated, so we set the variable for x, y, and z and compute for these three variables directly, and this is our result. So if we plug these back in, we have completed our search for R, which is this matrix over here. And this is question 3 finished. And now when we move on to question 4. So in question 4, this is a clear example as to why is our big Q so important here. You see, what is our big matrix, big Q matrix? It's in essence an orthogonal matrix. That means every given vector in our big Q is 1, orthogonal, and 2, units. So we can actually derive that property as a mathematical equation shown here. So this what this is saying is that given any two vectors in our big Q, our assumption here is that xi and xj, it belongs to our big Q. So if we take the any vector transpose with another vector, the results are either 1 if I is j, which is we are taking the same vector 2 times, or 0 if these two vectors are different. Why is that? Because since our vector is a unit vector, so the length should be 1, right? So this is exactly the result. And since our vector are also all orthogonal to each other, so it is also 0 if we take two vectors product. So what does this imply? It implies that Q transpose Q is in fact I, because 1 would only remain in the main diagonal of our Q transpose Q, and the rest should be 0. So now, armed with this knowledge, we can just compute for x directly, which is this equation here, as I have derived before, replacing, but the twist here is that we replace A for Q. So we end up with this equation here. And since Q transpose Q is I, and I transpose it is itself, so we just scratch this out, and all that remains is our Q transpose B. So what is useful about our big Q is that it's very useful when we want to calculate our least square solution. So because we don't have to compute all these ugly inverses if we have Q, it's just an identity vector. So this equation will be greatly simplified to our Q transpose B. That is the significance of Gaussian reduction and our Q. So that's all for this lesson, and I hope that through these explanations you have a firmer grasp on those various concepts, and I'll see you later. Peace out.